morning. We resume what we were saying last time about materials. So this course concerns material science, so the fundamentals of material science. You may know that materials science and technology are connected. Our course is more about materials, so the type of materials you have. You have materials which are developed in nature. There are materials which are synthesized. They are different in the sense that we tend to think to produce a material as a whole in a structure, which might be a tube or a laminate or another molding, like it is the case for plastic with complex shapes in some cases. Whilst nature acts in another way, it uses a limited number of materials. Nature doesn't use metals. It uses a lot of metal oxides, ceramics. It uses proteins. It uses derivatives of sugars, therefore polysaccharides. Having said that, nature has also a different approach in terms of building materials, because it builds materials into a hierarchization process and philosophy, which is a trick that allows nature to confer to materials and to structures a number of properties which we are not able so far in most cases to obtain. We stopped last time by saying that nature is able to self-assemble materials, for example, so to start from the cell, from the molecule, even below the cell, from the molecule. So if you build a structure in polysaccharides, like a natural fiber, a vegetable fiber, then you start from the glucose molecule. And then gradually you build larger structures. And in another sense, glucose molecule is embedded in your structure, but you don't see it anymore because you build greater, larger structures. And in the end, you have some characteristics which are essential to the life of natural creatures. Because I would say you are able to repairing, to add sensors. One of the problems, for example, in material science is that we would like to add sensors to our materials. Sensors to sense temperature, to sense pH, therefore acidity, to sense elongation, deformation. But in most cases, we need to apply them as a separate material, possibly gluing them. You can bond, for example, a strain, therefore a deformation sensor to your material. It's not the procedure that nature applies. Nature has the possibility to embed the characteristics of the materials inside it, therefore sensoriality. Therefore, the idea is also to design for function, and the repair, self-repair is connected to design for the function, because when you repair something in nature, it hasn't exactly the same shape it used to have. Like bone, when you repair bone, it doesn't have exactly the same geometry, because it builds on repair, on repairing the surface or repairing the structure. As you may know now, I have proposed you to read that book, which is Understanding Material Science. That book stops in 2005, obviously, because it was edited at that time. It's a very complete book. I will give you more advanced development of the last 15 years in material science. It's happening a lot in material science during the last decades, especially because we are involved a lot into sustainability, into building materials which can be sustainable, therefore not harmful for nature. Apart from that, the approach of the book is still very actual because it builds together with history of materials. And history of material science, it's an history, as I was saying last time, of material substitution. We use it to make something with some materials. Now we use other materials to make the same thing, the same object. For example, as I was saying last time, I was making the example of the bucket. You can make a bucket into steel or a bucket into plastic. Or you can make, for example, a fork into metal, or you can make it into plastic, or even into bamboo, for example, which is a kind of wood plastic. You find out a material which is intermediate between wood and plastic. We are going to discuss that later on. But what is important is that once you have materials, you may have the need to apply some coverage to materials, some coatings, for some particular reasons. You may know that one of the main principles is that we define materials as something which is able to withstand a force. And this is going to be crucial, especially in the lecture I'm going to give on Monday. We will concentrate on forces, on the nature of these forces and how they affect materials and how materials are able to withstand them or not. Therefore, how materials are able to break. The question is that materials are often covered with other coatings. For example, I'm showing you here some examples. You know that, for example, mirrors are made with glass, and everyone knows that, but below glass, a coating which is usually made in silver, therefore in a metal, allows you to reflect light and therefore your image into the mirror. This is a coating which is essential for function. We don't expect that the coating alone would withstand the force, but the coating is applied to perform some function, to give to this structure a function which it didn't have in the first place. There are other cases in which you apply a coating for other reasons. For example, anodization. Anodization, it's very diffuse for aluminium in particular and titanium as well. Although aluminium, it's more diffuse also because it's cheaper than titanium. The question is that anodization, which might be colored as well, because we may add some metal oxides color materials, which is well known from glass. We are going to talk a little bit more about glass later on. Anodization means that you try to avoid one big problem that metal have, which is corrosion. Metals tend to corrode, and the problem is that the corrosion takes place because the oxide layer on metals, like it is the case for iron and steel also in some cases, tends to be detached, therefore exposing further parts of the metal to corrosion. The parts below are exposed to corrosion, and in the end, corrosion gives you the idea that the material is consumed in the end and tends to be destroyed by itself. Anodization It's a good process because it exploits a characteristic of some metals like aluminum, like titanium, that the oxide is stuck in a reliable and fixed way to the surface. So in the end, you have this oxide, but you don't have corrosion. The oxide protects the bulk of the metal. We can push that process further on, and we can increase the thickness. It's always a matter of tens of microns and so on. You can increase the thickness of the oxide, and it's always stuck, and it's protected. Since it's thicker, it's even more protected. It doesn't expose the further surface. People, students of chemistry, but also the other students, may know that the anode is the pole in which oxidation takes place. So anodization means that we allow the metal to be oxidized more and more until we reach a definite thickness. This is a kind of protective coating. There are other kind of coatings which are interesting, which have become of more and more interest. For example, the super hydrophobic paints. Super hydrophobic means that it's more than hydrophobic. Hydrophobic doesn't absorb water. Super hydrophobic repels water, which is more than just not absorbing it, because you may have water which is not absorbed but stays there for some time and may generate also some problems. Thinking of paints, well, it's obvious that if water stays there and the paint is moist, it's humid, then you find out that further problems may arise, and the paint might be damaged, the color may fade, and so on. Therefore, you would need, in some other cases, to have a super hydrophobic behavior. The super hydrophobic behavior, we are going to discuss it later on because it is very central to some problems in materials. It's inspired to a plant, the lotus. Lotus effect, the so-called lotus effect, means that water droplets fall down the paint, fall down the surface in a very quick way because they tend to assemble into spherical surfaces and tend to go away. This is a coating again, which has another function. Another important function of coatings, which are not structural materials but may be applied to structural materials, is of course bonding. You may have adhesives which are applied to materials in order to make them adhesive or make them self-adhesive, so therefore adhesive to themselves and to seal the material, the structure. And the problem of glue, the problem of adhesives, it is central, for example, when we think about sustainability, because in many cases, sustainability it's affected by the fact that we apply a glue and we are not able anymore to remove it at end of life. So the best, thinking of end of life, the best idea in order to recycle the material would be to have a single material, just one material. If it is steel, it's just steel. If it is plastic, it's just one type of plastic, say polypropylene. If you have another material, it can be tricky to separate these materials. In case of adhesives, glues, and so on, it might be even more critical because, of course, glue is made to bond materials, and detaching at the end of life goes against its function, so it might be difficult. I'm saying all these things because I would like to entice you into some materials research teams. There are a number of teams into materials research. And if you get curious about one of these, you may start going deeper into this. Of course, the number of hours we have is limited, and we are trying to do what we can, because it's a large field, material science. It's also multidisciplinary. So what it's important to understand is that the history of materials was starting some time ago, a few thousand years ago. One of the first, I would say, material science texts comes back to Homer, to the Odyssey, when Ulysses came back to his wife Penelope, and he wanted him to be recognized by his wife, and the best thought of was to recount, to narrate how he built their bed. And of course, the bed was made of wood. Was made of the material he was able to trace down in Greece. So basically, wood, olive wood, which is not one of the most popular woods. Then some metals, precious metals, gold, silver, and bronze. Bronze was used. We were at the Bronze Age, and bronze, which is an alloy of, as you may know, an alloy of copper and tin. Bronze was had a temperature of melting, a melting temperature which was below that of iron, and therefore we had first Bronze Age basing on steel, on copper, and then the Steel Age, and the Iron Age, which evolved then into steel. Steel is much more recent to be made into an organized way. Steel comes back to 1700 around. So beginning of the Industrial Age. What we were using before was mainly iron. Apart from that, there were other materials. There were some ceramics, ivory, which were taken from animals. Basically, they were taken from horns, basically, and from elephant horns, and in other cases from other animals' horns, even from bovine horns. But this wasn't ivory, but it was really horn. So it was different. There is a difference between them, also in terms of chemical formation, chemical characteristics. Then there was leather. Leather was made of skin of oxes, basically of cows, and purple. Purple was a color. These were the materials that Ulysses had available at that time. Not very much, because of course, if he had steel to work his bed, it would have been much better, but he didn't have steel. But it is important anyway, because this is the starting point of material science, and it's important not only from an historical point of view, but also from the point that we are back to try to use in an updated way a number of materials which come from nature, because of course materials coming from nature tend to be biodegradable, which doesn't always mean that they are completely sustainable in a modern way, because they might be treated. For example, leather, it's heavily treated with chrome salts. So this may present a problem. But anyway, we are coming back to natural materials for some application. And this is another theme, big theme of material science, and which is articulated in a number of possibilities, in a number of challenges. For example, textiles. You may have heard that textiles are an effect of the textile industry is one of the most polluting industry, especially because of microplastics, because most of textiles we use now are polyester. And polyester tends to be gradually destroyed, even in the washing machine, but also during processes, during manufacturing processes, we lose a lot of plastics and microplastics and so on. Of course, at that time, in the beginning, they were using basically silk and wool. Coming back to Ulysses' time, they were using especially wool. Silk was to come, and they had some fibers. They had some fibers which were already starting to be used, like line and like hemp. But with very different characteristics with textiles that we use to know now. The question is that a number of materials were available for painting. So basically, animal or plant extracts. One of the most popular ones was, apart from purple, the dyer's wood, which is very known as a blue color. Blue color was quite difficult to be obtained because plants tend not to be blue because of it is the color of the sky. But there was this dyer's wood, which is the traditional color of the garments of the Holy Virgin into the Christian tradition. And therefore, it has a long, you may understand, it has a long history. And other plants, yellow, obtained by the reseda, which is another plant. It is important, I'm showing the reseda here because you may see one thing which is very important, that textiles tend to have different colors, slightly different or heavily different, depending on the type of textiles, the type of coloring, the type of plant, depending on the type of textile and on the type of plant, depending on the pH. You may have higher or lower acidity and then find out that the color is different. A rough rule would say that the more acid an extract, coloring dye, the more acid it is, the reddish it is, the more reddish, close to red it is. Then we have the cochineal, which comes from small insects and is still used a lot, for example, for liqueur and so on. It's a kind of coloring extracts which is heavily used, well, not only for liqueurs in patisserie, and also for coloring the textiles. Of course, we have more chemical coloring dyes, which we are going to discuss later on. But we need to focus on the fact that there might be natural options, not just because we love the environment, but also that we want to protect the environment, but also for the fact that we would like to have more sustainable options. Okay, so these were the options that were available a few thousand years ago. Some of these are still used now. And what about materials? Well, we were saying bronze. Okay, bronze, it's an alloy of copper and tin. Of course, you may imagine that you don't find bronze as it is. You find copper and you find tin. You are able to extract copper and tin from the rocks, because in nature you don't find metals as such, but you find metals into rocks. Then we could discuss which kind of rock is more likely to embed a kind of metal. There is a connection between the type of rock and the type of metal, because in most cases rocks are oxides or carbonates or sulfates of a determinate of some metal. We don't know exactly how they were starting to produce bronze. There are some hypotheses which are interesting anyway. There are, because possibly all these hypotheses are true, because they were producing bronze in different ways. You could either melt a mixture of metallic tin and metallic copper. Tin does melt at low temperature, a quite low temperature, and it is interesting as well. That's why tin and lead were used a lot until the 1850 and so on. Then they have not disappeared completely, but they are used less because they have other problems. For example, they don't cast in a precise way like is the case for tin, and lead could be poisonous. If it leaches into water, it is poisonous. So they have problems, but they melt at a low temperature, so it wasn't a problem for tin. And copper, even if its melting temperature it's higher, was able to melt anyway with the means, with the instruments they had at that time, over 2,000, 3,000 years ago. Or you could add some tin oxide, some cassiterite, to already molten copper. So you melt copper, which is the tricky thing. Then you add some tin oxide. Or you smelt the naturally from a ore. A ore contains tin and copper, and you melt it naturally. This is, I would say, this is the a bit less likely, but it is interesting anyway. They have archaeologists that find evidences of all of these processes. Then you could smelt copper ore together with trachyterite, with tin oxide. Smelting means that you put in a kind of furnace, which was a very simple furnace made with stones, even before the invention of bricks. So basically, it was made with stones and kind of groups. I would say more than saying to a pile of stones. You group some stones by size and try to make smelt the material, the rock, to obtain that bronze. So in the end, the interesting thing of that is that gluing, bonding, was starting even at that time. Here we have turquoise. Here we have turquoise, which on a sword hilt, it was bonded, it was glued on a sword hilt, so to keep the sword, and the turquoise was also a precious stone, and it was they were a number of stones were put and glued into the sword hilt, with the idea that it would not only give more value to the sword, because it was a sword which wasn't used by a simple soldier, but probably it was its goal, it was to be given to a king or some person of importance. But apart from that, it is interesting that they started using as glue beeswax, which was a natural material they had available, and it glued very well. It glued so well that we found it intact after more than 2,000 years. So beeswax, it's a possible glue. We will consider adhesives, we will consider the types of the adhesive materials, which are numerous. And there are, as always, there are natural, there are synthetic, there are new glues, new adhesive layers, which are developed every time. While the research is going on a lot about glues, because glue is a critical element, as I was saying before, because it is a substrate. At the end of life, it has to bond well, and at the end of life, it has to be detached. This is not a problem with the beeswax because it's degradable. It is a problem with synthetic glues. Beeswax, it's a material that has been researched for many years because it's available. It works. It is an ester. Basically, it's a paraffinic ester, as chemists may know. And then it's used still now for example, to produce microspheres for incorporation of medical drugs. This is an example of one of the latest research on beeswax. To make some microspheres, you know that there is a lot of research about releasing drugs in a controlled way in our body. The problem, you could take a pill, of course, you could take a pill, but the pill means that the value of the medical drug, the amount of medical drug you have in your body increases, then decreases, and you take another pill. It would be better a controller release. In fact, they are studying a lot with these microspheres, which some can be made even by beeswax, to incorporate medical drugs and to release it gradually into the body. To some condition, we are able to, well, it's not toxic, beeswax. We can't eat large amounts of that beeswax, but anyway, in these amounts, it doesn't create any particular problem. And this is considered again as for sustainable material, as I was saying. So there is a lot coming out in the last few years that reconnects to the old history. There are things which are very technological, but there is always an history of there is an history of material science which we still consider and gives us lots of ideas. As I was saying, other possibilities with beeswax, for example, these are some licensed products which were developed in the last few years. In the last few years, for example, for packaging, there is a lot of research on sustainable materials. For example, this is Upper Pack. It's with bees. It's an Italian licensed product about beeswax and cotton gauze. Cotton gauze, it's a newer product in a sense. Cotton had development from the 19th century on. It wasn't really used that much into before that in ancient times, because it wasn't very compliant, very resistant. We will discuss that later on about talking about natural fibers. This demonstrates that beeswax can take other forms, can also be embedded in a film, in a packaging film, in a packaging film suitable for food packaging. Food packaging is investigated a lot into the development of material science. Other food packaging, these are other examples. This is a starch film. In the lowest part of the slide, you see a starch film. And a starch is a polysaccharide, a derivative of glucose again, but more gluey, more less structural, I would say, at least to start with. Then it can be made into structural films and so on. And it can incorporate eggshells. Why eggshells? Eggshell, again, it's a calcium carbonate egg, the eggshells, but it might be a waste. This illustrates you a problem which is becoming very important, the incorporation of waste into materials. I am personally researching a lot on this, and you will see that the problem of making something from waste is becoming crucial because we want to have a circular economy. Circular economy means not have any longer waste. So waste needs to be given an opportunity. Giving an opportunity means that you can mold it into new materials, so elongate its life, so its life becomes longer, and it might become waste eventually, but in the meantime, we have extended that life, we have removed the problem, and we have given value as well. We call this process upcycling. Opposed to recycling, upcycling means that we don't produce a material and a structure with lower value, but we give value to something which has no longer value. Waste has no longer value. That's why we give it value. SCOBY skin, SCOBY, it's the residue of a tea, a type of tea, which is called the kombucha. And you can make a kind of leather, kind of false leather. Because as I was saying, Ulysses was working on leather, using leather because he had these skins from cows, etc. Even from other types of cattle, but like sheep, etc. But the main question is that this needed to be treated with unsustainable materials like chrome salts, especially potassium bichromate. And this means that now we would like to produce false leather that works like leather, but it's produced from biodegradable substances, biodegradable materials, and SCOBY skin is good for that purpose. These are three of the countless examples of these attempts to produce new materials using some waste, some natural materials. Okay, then ivory. What is ivory? Ivory, it's calcium phosphate, so basically microcrystalline apatite, and which deposits into a hierarchical structure of protein fibers. We talk here a bit more about proteins, about collagen. You may remember that collagen is the building molecule of bones, the building structure of bones, which are arranged in a triple helix structure. And here we have again a glue. Protein fibers work as a glue, and collagen may itself work as a glue. And they cement together that structure of made of calcium phosphate with some calcium carbonate. Here again in ivory we have some hierarchical structure which starts from collagen, of course. Then the collagen fibers are arranged in different ways. Remember that in materials we call fibers something which are sufficiently elongated. They have a sufficient ratio between the length and the diameter, at least 10, I would say, at least an order of magnitude to be considered fibers. Otherwise, we call them particles. So basically, we have in composites, we have fibers or particles. We have composites reinforced with fibers, so matrix reinforced with fibers, and matrix reinforced with particles, or both of them. We can have also both of them in some cases. The world of composites is quite complicated. You may remember the composites, it's an hybrid of the three main types of materials. So you have a ceramic matrix composite. So the matrix, the bulk of the material, it's a ceramic, a calcium phosphate. And then you have in between some collagen fibers, which bond and hopefully reinforce. In reality, they reinforce in the case of ivory. Then you can have horns. In horns, the matrix, it's no longer a ceramic. It's a protein again. The matrix, it's a protein which has ceramic characteristic, but it's not a real ceramic. You have these proteins, which is the most diffuse protein, the one which is used in hair, nails, and so on, and it's bonded by other proteins, other proteins like other proteins. In that way, you have a full protein, an whole protein structure. Yeah, you have an whole protein structure. You have an whole protein structure, and this whole protein structure. Sorry, you have this whole protein structure. This, of course, means that it's more compatible. More compatible because if the materials are chemically similar, you may remember that you are able to solute, to dissolve the similar dissolves into similar substance. And it is the same case for composites. So if you have an whole protein structure, protein into protein, then you have a better compatibility. In fact, it is a material which is, despite being a ceramic, it's not very brittle. It's a material which is quite strong, able to withstand forces, not being very brittle. We define brittle something that breaks in a sudden way. But anyway, we will build on that on the next lecture. Having said that, what they were starting at the beginning, they were using plants. Even at the time of Ulysses' time, which is our reference in a figurative way, I would say. We imagine that material science starts from Ulysses. It started even before, even by carving stones, and that text from Homer gives you an idea of what was used at the time. There are other texts in other cultures that make the different things, slightly different things, like in Indian or in Chinese culture, but basically the approach was to start from materials obtained from nature, therefore wood, proteins, other plants other than wood, and some ceramics and metals which were started to be used, to be smelted and obtained. One of the first items that has been used and has been developed was paper. Paper history, because it's one of the materials that survived, like glue. Glue survived because it has an essential. Paper as well has got an essential function. They started building by some plants, some plant leaves, using papyrus plants like meat, and they were gluing them with some natural extract from the same plant. This is very to glue something with an extract from the same plant. It's completely sustainable. First of all, well, in fact, we found some paper strips, papyrus. In fact, the name paper comes from papyrus. Bonded, the same glue, which are still intact after 2,000 years or so. Then they were hammered, really hammered by a stone, and together to form some, to glue with the natural sap to form some real strips, which could be useful not just to write, but also gradually it became more and more important also to paint on it as a support for painting. And gradually paper expanded its field of action to packaging. Paper now is used a lot for packaging, which creates some environmental concern and so on. But anyway, that's important to know that paper is one of the material we brought from our old history of material science. It's still very actual material. Some other kind of papers were made from or particular sheep skins, like the ones which they were, and but we will the parchment, which we will expand on a bit later on, because paper history is very interesting because it gives you the idea of the possible mechanical, chemical, and physical modification a material can undergo without losing their properties, because paper is always suitable for this function, although it has been obtained by a number of different plants, by a number of different methods, and it has been also colored in a number of ways, etc. And there is a question of paper degradation, which is very suggestive for materials degradation. Degradation means over time and by the action of chemical agents. Okay, then we need to concentrate on something more physical. After we have done this discussion on the force and in general terms, so we have structural materials which are able to withstand some force. We have done some excursus on what was done in history, the point where we started from. Now we need to concentrate on elasticity. I don't want to go to give a suggestion that you wouldn't know that these things, because these are very basic things. But it's better to remember. It's better to remember that we mean as elasticity, a material is elastic in the case we apply a force, and then we extend it, so we have a spring. We start from a spring. A spring, it's an example of something that can be extended by an applied force, and then it rebounds completely if the spring is elastic. This is true in most cases for springs. Over time, springs tend not to be elastic anymore. The opposite of elastic, although I will repeat that a number of times, the contrary of elastic, the opposite is plastic. If it doesn't rebound completely, if it doesn't come back to the exact shape it was, it is a little bit plastic. So we have a force, F, we have an elastic constant, which depends on the type of material of which the spring is done. Most springs are in metal, but there are now nylon springs, so plastic springs. And of the geometry, there are a number of geometries of the spring. Next time on Monday, I will talk a bit also about the geometries of spring, because it is suggestive also of our needs, so the way we apply materials. It is a fair assumption to say that if we want to apply a sufficient force to materials, they need to be elastic. Most material needs to be elastic. There are some materials which work anyway if they are not elastic. If they are viscoelastic, so they have a behavior which changes over time. or if they tend to plasticize over time. This is, for some material, this is not a big problem, like for plastics. But in most cases, for having very strong structures, we need elasticity. Okay, so we have F equal to K, the constant of the spring, X, which is the deformation. And we suppose the deformation comes back to the initial dimension. So we have X and we have a delta X, and then we come back to delta X equal to 0 when we remove the force. This is elasticity. Okay, then we come back. I wouldn't carry on very much after that, but this is very crucial. This is a crucial slide, not because the previous one weren't important, but we have to concentrate on that. Material science, even if the use of materials and materials technology dates back 2,000 years and more, 3,000 to 4,000 years, when the real material science started, so when we started to make sense of all of this into a science, into a multidisciplinary science, the idea that was developed, so we are around, now we are around the end of the 17th century, around 1700 year 1700, when they started to investigate the fact that there could be a material, building on the fact that elasticity was a good thing to apply a force to a strong structure. There was an ideal material. So, of course, the first characteristic was that an ideal material was elastic at every time in its existence. So we apply the force, and then we apply a force a number of times, and it always rebounds back exactly to its initial dimension. There are two other characteristics for an ideal material. Remember, please, that as every ideal, as the ideal gas, or any ideal, even an ideal person, the ideal doesn't exist, doesn't fully exist. You may imagine that it exists, or you may consider that there are some materials that are close to the ideal, but an ideal material doesn't exist. And I'll show you briefly also why it is so. Anyway, other two characteristics are that the ideal material would need to be homogeneous. Homogeneous means the same density in all its volume. So we may make some assumption. A composite material cannot be homogeneous because it has got a matrix with its own density. For example, carbon epoxy, you have the density of the epoxy resin, and you have the density of the carbon fibers, or particles, or short fibers. They are not very far, the two densities, but they are not the same. So this is not homogeneous. Plus, an homogeneous material would need not to have porosities, voids, lumens, as it's called, they are called in natural fibers, in botanics. So a vegetable fiber is not homogeneous. A ceramic is porous, is not homogeneous. And then the third characteristic is that would need to be isotropic. So what we saw before, elastic, homogeneous, needs to be true for every point in the material. If you assume that the material is a cube, well, the solid which is to be considered the ideal one, it's a cube, would be a cube, where all dimensions are the same. We consider that every point in the cube has got the same properties. The same properties, so in, of course, in direction X, Y, and Z, but also in every point. This is, again, this is not true because, as you can see most materials are used in shapes which are away from the cube. So they might not be isotropic. Not only homogeneous, not only elastic, but they are, of course, not isotropic. Because if they were, there would be an exact direction in which to use the material. And this is often the case because you use tubes, you use fibers, you use textiles which have two directions. Well, in some cases you use cube. For example, concrete. You use cubes of concrete to make some construction. You can make bricks of clay, made of clay, which are sort of three-dimensional. The real problem is that you have porosities, lots of porosity. We can easily say that we have no ideal material. Why do we study ideal materials there? Then, because we are able to make assumptions by taking this ideal and see how we are far from the ideal. There are materials which are more homogeneous, there are materials which are more isotropic, and they are selected for that reason. There are materials which are more elastic, and this influences the choice of what to do with the materials. We make a choice to do something with the material because we know that it has some characteristics which are closer to the ideal than others. Okay, then another important thing is that you see at the end of this slide, and left, I would say, you see that you have this force deformation graph. So basically, this is really very basic. So you apply a force, you get a deformation, which is good. This means to be elastic. You have your spring, you apply a force, and you have this deformation, and then you are able to calculate the energy when the material deforms. I assume you know that you have this mechanical energy, this elastic energy, and you may consider that if everything is elastic in its behavior, it's elastic for all the time I apply that force. I have this triangle which represents an energy, which represents an elastic energy, and we all know that. It's important, therefore, also the area under this graph, under this, well, it's not a curve, it's more a line because it's completely elastic. And this represents the elastic energy, which is given to the material, and then it's recovered. So you know that you apply some springs because it's able to store some elastic energy, which is obtained as from the triangle area as half F multiplied by V. So this energy, which is a work, basically a mechanical work, it is interesting that the material is elastic because there is a proportionality between the force and the deformation. This wasn't discovered until the end of the 17th century, until Hooks has done some studies on that. Before Hooke, also Leonardo da Vinci is known to have tried to pull a beam and to remove then the force, and he wanted to find out if there was a proportionality between the force and the deformation, because his idea, it was that there should have been some proportionality between the force and the deformation. In reality, didn't find it because he used wood, and wood, once he removed the force, got inflected, and then it wasn't clear at all that there was this precise relation between force and this linear, I would say, relation between force and deformation, because wood got a bit plastic during the time that Leonardo pulled it. It is interesting because Hooke instead, Thomas Hooke, did that with steel, with iron. It was in the way of getting the steel, because from iron and steel there is a bit of difference. Iron is basically extracted and is cast into molds. Steel has got a controlled amount of carbon, which wasn't the case at Hooke's time. But anyway, even with iron, it got clearly the idea that there was a relation between force and deformation. Then that elastic materials were able to exist. And I am not sure in nature. In nature, it's difficult to find something that is completely elastic, but humans were able to produce elastic material. This was a strong point, a standpoint on the development of strong structures. Think of buildings, think of ship, think of trains and so on. So this was a standpoint. Even if trains and so on, they were at a long time before they would come, because then you needed the machine, the steam machine, and which was developed around 100 years later by James Watt. But apart from that, we can say that I've said all this to say that metal steel, is quite close to the ideal material. That's why when we start investigating material science, we always start from steel, even if we are not using steel, but we start from how steel behaves, and then we see our materials are far removed from steel. You may be using steel as well in the first place, but you may be using aluminum, you may be using plastics, you may be using concrete, and they have different characteristics from steel. Something it's close to steel, something is more removed from it. So you may remember the material from the course. What I would like to say before leaving you is that I put the slides number 1, so this one, the file number 1, into my page in the website of the part of the school. And I'll put before Monday, even today, I think, the file number 2, which will concentrate on mechanical testing and on how we build on the fact that we have decided what an ideal material should be. It doesn't exist, but we want to investigate materials building on that. And then I have the recording of the last lecture and of this one, which we are completing, which we will, I will put again on at least as a link into my page. As I was saying, it's well, it's a bit possibly early to say that, but try to more than remembering all things that we have said, it's important that you get curious about things we investigate and we try to focus on, and on the topics that research in material science are working on, which change year by year. But apart from that, apart from the huge development of materials, if you look at patents about materials, these are countless. Every year you find out that a number of new materials, or possibly old materials rebranded and redeveloped and so on. This applies to plastics, this applies to nanomaterials, this applies to materials with particular properties. You may remember the first time we have talked about metamaterials. We have done some hints, some suggestions on metamaterials. I will talk of that later on, after we have some grounds on which we can build this kind of knowledge. But the question is that there is a lot of developments into materials research. Some of the materials get to the industrial stage. Some other materials remain as concepts, as prototypes, and so on. They are important anyway because they suggest there is a problem. For example, sustainability might be a problem, or the achievement of some kind of characteristics of possibilities for the materials. For example, drug delivery, it's a challenge. It's a challenge, and there are materials which are aimed for this to obtain this goal, to overcome this challenge. And there might be very highly technological challenges. There might be other less technological but important anyway challenges, like obtaining a sustainable food packaging, for example. You may not consider it very technological, but there is a huge market around this, and you may be asked possibly to develop a sustainable food packaging, possibly even using waste from other materials. Anyway, I was saying already last time that you are going to write this kind of educational paper. Educational paper, as I was saying last time, is something about materials, a topic into materials, to be given to someone that doesn't know much about materials. So you need to be as simple as possible. Please don't be offended by the fact that we want to keep it as simple as possible. I'm trying very hard to do that. Because it's very important that as a multidisciplinary field, everyone is able to understand a little bit what's going on into materials. Also because in our day-by-day life, we are all affected by that. We can discuss about this later on. You can please feel free to send me emails. I haven't seen many of you sending emails to get the materials. I mean the file number 1, which anyway now I have put into the school web page, but now to my personal page into the school website. But it's important that we keep in touch also because we are in this situation of online lecture. We don't see each other in person. Please feel free to send me an email and to propose possibly some themes you would like to investigate. We are not going to have the time to talk about everything, but we can have a method. Possibly we could start, you can start, for example, if you are interested in, say, viscoelastic materials, you could go into Scholar Google and see what you find out. You may find out that you may not suspect that you find thousands of papers. Even if you look at a material which seems trivial, like beeswax, you ask for beeswax, and you try to concentrate on what concerns the use of beeswax as a glue, as a material, as a coverage, and so on, and you may find out that you find again thousands of materials. Then it's a question of selecting, becoming more selective about what you would like to know about your material. And to discard all the information which brings you too far from the objective. So to concentrate on material that can be really educational, that can lead you to an educational paper. When I say educational, I don't mean a scientific paper. Please, again, don't be offended by that. But educational paper, I've seen in my experience in material science that in most cases we write papers, but it's important that we get people to know what is the issue that leads us to write this kind of paper on this kind of subject, why this subject is important. If I am studying, say, ivory, why I'm studying a modern use for ivory replacement? Because, for example, now there is the question is that you are not going to catch elephants anymore to get ivory, which is very good. That means although that you need to find an ivory replacement, a replacement for ivory that works as well without killing elephants. This might be a big challenge, and there are lots of people working on that. This is the same for leather, false leathers. This might be the same for horn and for other materials. Then there are some other materials which work well than other, or which are almost exhausted, for example. For example, you may consider antimonium. Antimonium is used in cell phones, say, as I was saying last time, possibly, and it's almost exhausted. And so you can pose the problem: what can I use to get the same properties instead of antimonium? Material science is an history of replacements, of skillful replacement of materials, because we don't replace materials with any other materials. We replace materials with materials that would work as well. In some cases, we don't succeed. In others, we do succeed. We don't succeed, but we try again. That's experimentation. That's all about experimentation. So, okay, we will see again on the same mode on WebEx on Monday at 4, and we will concentrate on starting understanding how we test materials and how we get properties, how we get numbers out of materials. This is a tricky question, but we need to start to have some ideas, because we'd like to have numbers to evaluate materials, to evaluate their properties, starting from mechanical properties, because in a sense, these are the simplest one, the most useful one for structural application. Okay, thank you. I'm waiting for your, of course, email, and please feel free to contact me at any time.